In this video, we're going to talk about constructing a confidence interval for a mean. So we will construct confidence intervals to estimate a true population mean. We will focus on the case when the true population standard deviation is not known. This is the more useful case. If you don't know the true mean, then you probably don't know the true standard deviation. There is a slightly different process if you do happen to know the population's standard deviation. That's actually a bit easier, so we're not going to do that process, and in practice it's not as useful. So we're focusing on the case when the true population standard deviation is not known. And this is similar to the process for constructing a confidence interval for the population proportion, as we did in the previous videos. There we used the sample proportion to construct a confidence interval for the true population proportion. Here we're going to use the mean from a sample to estimate the true population mean with a confidence interval. So we want the true population mean. Remember, that's mu is the true population mean. Like, if we're talking about weights of border collies, there is some true population of the weights of all border collies in the world, but we're estimating it with a sample mean. So we take a sample of some number of border collies and find their average weight. X bar is the sample mean. So we find X bar, the sample mean for those weights, and we also find the sample standard deviation for those weights, S. Remember, lowercase s is the standard deviation of a sample of data, as opposed to sigma, the standard deviation for a population, which again, we don't know. So this is going to look like a confidence interval, the sample mean minus some margin of error to the sample mean plus some margin of error. So now we just have to figure out, how do we find this margin of error? Remember that when we were doing it for a proportion, we found that the margin of error E was equal to Z times sigma, where sigma was the standard deviation and Z was the value that separated whatever percentage in the middle from the rest. So if we were at either a 90% or a 95% or a 99% confidence level, then Z was the value that separated that value in the middle, that percentage of data in the middle on the standard normal distribution, from the rest of the data. When we estimate the population mean, instead of using the z-score chart or the standard normal distribution, we're going to use what's called the t-distribution. It's also called the student t-distribution. The reason that it's called that is not because you all are students and learning, but it's because the person who originally discovered or created it, Gossett, was working for the Guinness Brew Company to test beer quality, and he realized that he needed a more conservative distribution because there was less information known, and so he developed this t-distribution, and because he was working for a company with intellectual property laws, he wasn't actually allowed to publish it, but he really thought it was important to get out into the world, so he published it under a pseudonym, the pseudonym Student, instead of his actual name, so that he wouldn't sort of get in trouble. So that is why it's called the student t-distribution. So the student t-distribution is very similar in shape to a standard normal distribution. So here is the z-score distribution, the standard normal distribution in blue. And if you can see, if you compare like the tails of the standard normal distribution to the tails of the t-distribution, there's more area in the tails for the t-distribution, and basically this is a more conservative estimate where we're less confident about where the data falls. So this data is more spread out to make room for more uncertainty based on having less information, not knowing the true mean and the true standard deviation of the population, but only having this information to extrapolate from a sample. And as you'll see when we look at the table, the value for t depends on the sample size, n, and as the sample size increases, the t-distribution gets closer and closer to a standard normal. So as n increases, this distribution for the t-distribution will be, come more and more close to a standard normal distribution for larger sample sizes of n. So in finding a confidence interval for the mean, the margin of error E is going to be equal to this value t that we'll see how to calculate in a moment, times the standard deviation. And what is the standard deviation? Well, we will always get a sample standard deviation S, but we're not going to just use that. We're going to use t times that value S divided by the square root of the sample size. Why do we do that? Remember from the central limit theorem that sample means are normally distributed. So sample means are normally distributed, and they have the same mean as the original mean, but their standard deviation is the old standard deviation divided by the square root of the sample size. As the sample size increases, the distribution of the sample means get closer and closer together, are packed in closer to the real mean, because we're taking, a sample and taking its whole average, and it's unlikely that those sample means will vary as much as individual data values. So E, the margin of error, is going to be t times S, the standard deviation for the sample, divided by the square root of the sample size. And again, that's based on the central limit theorem. Okay, so now we have to figure out how to find t. We find the value for t using a t-distribution table, and this value is based on two pieces of information. One is the degrees of freedom. So this is just the sample size minus 1. The degrees of freedom is just equal to n minus 1 or the sample size minus 1. The reason for this is it's like the number of free variables. So if you know the mean and you know n minus 1 of the data values, you can find the nth data value. But it's not important for you to know that. All you need to know is that the degrees of freedom is the sample size minus 1. The second piece of information that it's based on is the area in one tail, and that's based on the confidence level. So, for example, if we want a 90% confidence level, that means that, how much area is in one tail? Well, 90% confidence level, that's based on having 90% of the data in the middle. So that means that there is 10% of the data in the two tails together, or 0.1, 10% in the two tails together. And so in each individual tail, there's 0.05 of the data in each individual tail. So the area in one tail would be 0.05, would be this column if we were talking about a 90% confidence interval. And then if we were talking about, say, a 95% confidence level or a 99% confidence level, think for a moment about what the area in one tail would be in that case. Okay, so if we were talking about a 95% confidence level, that means that we want 95% of our data in the middle. So what is remaining on the two tails together? In the two tails together, there's 0.05 or 5% remaining. So in each individual tail, there's half of that. So there's 0.025 in this tail, 0.025 in this tail, and that's what we need to read this chart. The area in a right tail here is 0.025. 0.025 is right there. And if we're talking about a 99% confidence level, then we've got even less in our tail. So 99% confidence level, we need less area in the tail. And so we are going to then have 0.01 in total in the tails. And so in each individual tail, we have 0.005. 0.005, half of 0.01. So we have half of the remaining area in each tail. So 0.005, this is the area in the right tail in that case. And so we would be using this column if it was a 99% confidence level. and we would be using this column if it was a 95% confidence level, and we would be using, as we saw earlier, we would be using this column if it was a 90% confidence level. Let's do an example. So say we want to find a 90% confidence interval for the mean weight of border collies. In a sample of 33 border collies, their average weight was 43 pounds and their standard deviation was 6.3 pounds. Okay, so what do we have? We have a sample size of n is 33. We have an average weight, sample mean is 43 pounds. We have a standard deviation from this sample is 6.3 pounds. And we have a 90% confidence level. So 90% is the confidence level. So what we're going to be constructing is a confidence interval of the form x bar minus e, the sample mean minus the margin of error, to the sample mean plus the margin of error. So we already know the sample mean. Now we need to find the margin of error. The margin of error, as we saw before, is t times the standard deviation of the sample divided by the square root of the sample size. So we know s, we know n, we still need to find t. So t is based on two things. T is based on the degrees of freedom, and in our case, so the degrees of freedom is equal to the sample size minus 1. So in our case, that's 33 minus 1, that's 32 is the degrees of freedom, and also the area in one tail. So the area in one tail for a 90% confidence level, there's 90% in the middle, 10% in the tails. That means there's 5% in each tail, or 0.05 in one tail. So that means that we're going to be looking at this column, the column 0.05, and this row, the row with 32 degrees of freedom, and seeing where those things match up, and they match up here at 1.694. So that means that t is equal to 1.694. That's t. And now we can find our margin of error. So that's t, 1.694 times s. S was the standard deviation for our sample, and that was 6.3, divided by the square root of the sample size. The sample size was 33. And so then we can just calculate that margin of error, and our margin of error then would be 1.856 is the margin of error. Finally, we can construct the actual confidence interval, the sample mean minus the margin of error to the sample mean plus the margin of error. So we said that our sample mean was 43 pounds minus the margin of error 1.856 to 43 pounds plus the margin of error 1.856. And so our confidence interval is 41.144 up to 44.856. So that is our confidence interval for the mean, and that's telling us that if we took many, many samples of size 33, then 90% of them, 90% would fall in this interval from 41.144 up to 44.856. So we have a 90% confidence level that the true population mean of the weight of border collies is in this interval. Just one last comment about when this process is reasonable to use. So we can use this process to construct a confidence interval for a population mean as long as the data comes from a simple random sample and either the sample size is at least 30 or the population mean is, or the original population is normally distributed, or both things are true. This second requirement comes from the central limit theorem. When is it true that sample means are approximated by a normal distribution? So we won't really worry about these two requirements in this course, but just so you're aware, there's a sort of a minimum sample size requirement or knowledge that the original population comes from a normal distribution.